Welcome back to the course entitled Symmetry, Stereochemistry and Applications. In the previous lecture, we were discussing about the atropisomerism arising out of biphenyl systems. So, there we were talking about how to identify the R and S notations for biphenyl systems. So, here I had taken one example where one compound had two different substitutions as R1 and R2 being different, and we tried to identify their notation names by looking at those two molecules from two different sides. So, in the previous class we had discussed about how to find out the absolute configuration of the molecule 1. So, in this current lecture we will see what happens, how do we identify in the same way for the molecule 2, which is the enantiomeric pair of 1. So, if we draw this second molecule in the next slide and then do the same as we had been doing in the previous class, we will see how we can identify the absolute configuration of this molecule. What we had is the mirror image where the left hand side group was above and below the plane, carboxylic acid was above the plane and NO2 group was below the plane. So, we should draw the same here. So, remember that this bond which is drawn as dashed line is below the plane. So, now if we look at this molecule from the right hand side, what we see is this carbon should be numbered as 1 and the other carbon should be numbered as 2. So, on the front carbon, I think this should be corrected. This is not above the plane, this is actually on the plane of this projection. So, if we look at that front carbon, which looks like this, NO2 is up and CO2H is down, and those two are target pointing below the plane of this carbon atom to which it is bonded. So, what we should draw there as the dashed lines for NO2 and the dashed lines for the CO2H group, and then for the second carbon which is pointing towards me, but the left side is CO2H and right side is NO2. So, that NO2 is above the plane of that carbon number 2 and CO2H is also above the plane of that carbon number 2. And then when we try to identify the priorities, it is again based on the carbon number 1. So, 1 and 2, 3 and 4. So, this is 1, 2, 3 and 4. And now, if we see this wedge projection, which is very similar to the Fisher projection methodology, that these groups which are in the vertical line are below the plane of projection. So, in that case, we can straight away convert this into a Fisher projection as I am drawing here. So, this is 1, 2, 3 and 4. So, now if I try to identify the correct designation for this chiral compound, we should go from 1 to 2 to 3 is in the opposite direction, that is the anticlockwise direction. So, this should be S, but the fourth group is in the horizontal line. So, the designation of this compound should be R. If we just quickly go back to the previous slide, we can see that the enantiomer 1 was found to be S, and in the next slide we find that enantiomer 2 is having absolute configuration R. Therefore, the mirror image is an enantiomerically pure compound. So, if I do this from the right hand side as usual, what we would do is then change our reference. This first carbon becomes carbon number 1 and that gets carbon number 2. The priority order also changes because the priorities are given based on the front carbon. So, this is 1, this is 2, 3 and 4. So, now when we are looking at this molecule from the left hand side, what we are seeing is the molecular plane which is in the front is horizontal plane, and on the left I have NO2 group, on the right I have CO2H group, and both are pointing downwards. Similarly, for the second carbon, two groups are pointing towards me above the plane of carbon number 2, and the above one is nitro and the lower one is CO2H. So, nitro is here and CO2H is there. Now, if I quickly write down the priorities, this is 1 because this is on the front carbon, this is 2, this is 3 and this one is 4. If you look at this projection, you see that the horizontal line has bonds which are below the plane, the vertical line has bonds which are above the plane of projection. So, therefore, to convert it into Fischer projection, we should rotate the molecule by 90 degree and draw the wedge projection once again. I think this should be 4. So, now we can draw the Fischer projection of this molecule just like before. NO2, CO2H with 1 and 2, O2N and CO2H here as 3 and 4. So, if we do it 1 to 2 to 3 is anti-clockwise. So, this looks like S, but the fourth group is in the horizontal line. So, this is the configuration R. So, these two gives you the same configuration R. So, no matter from which side we look at these molecules, we end up getting the same absolute configuration. So, here I would like to give you the homework as this one. Draw the mirror image of this compound and identify the corresponding absolute configurations of these two configurations of the corresponding enantiomers. You can see that here the 4 groups R1 is not equal to R2, is not equal to R3, is not equal to R4. This is a type 4 molecule in this series, and you should try to find out what the absolute configuration comes out for this particular molecule. Now, let us move to the next part of this course, where we will introduce you to a different ways of notation of these chiral centers, which are formally called the D and L system of designation. This DL system of designation was first introduced by Emil Fischer. He actually identified isomers of glyceraldehyde, which has the chemical formula CH2OH, CHOH, CHO with one chiral center in the molecule. So, when he was working on this particular molecule, the chiral compound which was found to rotate the plane of polarized light to positive direction. So, which showed positive optical rotation. He labeled that molecule as D-glyceraldehyde, and the one which gives the negative optical rotation he designated that compound as L-glyceraldehyde. And then also he identified these molecules using his unique projection formula, the Fischer projection formula that you have already learned, and identified the 2 molecules like this. When the OH group is on the right hand side of Fischer projection, he identified the molecule as D-glyceraldehyde. And the other one, which is essentially the mirror image, he identified that as L-glyceraldehyde. So, this concept of designating D and L was then continued for a few years, and similar compounds having one chiral center were designated using these D and L notations. So, the compound which is having NH2 group in place of OH and a CO2H and CH2SH. This is called cysteine. This isomer was termed as L-cysteine. Similarly, this compound, which is the oxidized version of glyceraldehyde, was named as D-glyceric acid. And the corresponding L isomer had OH group on the other side. This was then extended to the class of compounds called alpha amino acids. So, in case of alpha amino acids and alpha hydroxy acid, this DL notations were also used. So, in that case, the top carbon in the Fischer projection was looked at for D or L designation. So, the compound which I am drawing here is one of the versions of tartaric acid, which has CO2H at the top and bottom, and you have hydrogen and OH here and OH and hydrogen there. This isomer of tartaric acid was designated based on the orientation of OH in the top carbon as L tartaric acid. Similarly, this compound, which is an alpha amino acid, had NH2 group on the left hand side and OH group here on the right hand side with a methyl at the bottom. Based on the orientation of the NH2 group, this was identified as L-threonine. So, this is how the alpha amino acids and alpha hydroxy acids were initially designated by D and L notations. And then this concept was also extended to the carbohydrate chemistry as well. So, in case of carbohydrates, the last chiral carbon of the carbohydrate in a chain was used to identify the D and L notations for those carbohydrate molecules. So, for the simplest carbohydrate, the glyceraldehyde from which it was started, when you have the OH group on the left hand side, hydrogen on the right hand side, you name it as L-glyceraldehyde. If we have two carbon atoms, two chiral carbons with aldehyde at the top and CH2OH at the bottom, OH and H here, and this also has OH and H. Looking at the last carbon atom in the Fischer projection, the bottommost carbon atom, this is also designated as L3os. And the other isomer of L3os with a different orientation of OH group on the last carbon was identified as the D3os. Similarly, if you try to identify L-ribose, it would be this one. And the other isomer of this compound is D-arabinose, which is this one. And the well known glucose, which is this one, was also designated using the D and L notations in the carbohydrate chemistry. So, once again, by looking at the bottommost carbon, this designation of D and L was given. So, we can see that by looking at one chiral center, the designation for the absolute configuration of a molecule was identified. So, certainly I am sure it is coming to your mind that this method has lot of shortcomings. Yes, of course, this has lot of shortcomings. It only signifies the chirality of only one carbon atom in a compound where you have multiple chiral centers, and if you have different orientations of this OH or this H or that H, keeping the same OH on the right hand side, it will still be called D-glucose, which is not correct. So, now if we see that if this D-glucose is oxidized to glutaric acid or aldaric acid, same product have two different names. So, if we have CHO, which is the starting point of this reaction, CH2OH, and we have OH, OH, H and OH, and here H, OH, H and H. What we are trying to do is we are trying to oxidize the CHO and CH2OH groups simultaneously. So, if you do that, what you end up is CO2H, at the bottom also CO2H, and we have 4 chiral centers where OH, OH, H and OH, on the other side hydrogen, OH, H and H. Looking at this molecule, considering this chiral center, we started with D-glucose. Based on that chiral center, the name of this should be D-glutaric acid. But then if I rotate the molecule in plane by 180 degree, what we get is this molecule. By rotating 180 degree, these two OH groups will go to the left hand side at the top carbon. Then the third hydrogen, which is here, will come here with OH there, and this will be OH. So, now in this case, by looking at this group following the same convention, gives me L alderic acid. So, this D and L nomenclature gives me two different notations for a given compound. So, there is a shortcoming related to this notation system. Now, if I look at a simple molecule like the plus tartaric acid, what is plus tartaric acid? The plus tartaric acid is CO2H here, CO2H down, OH and H. If we consider that this is alpha hydroxy acid, then we should give priority to this group, which is at the top position of this Fischer projection. So, this should be termed as D tartaric acid. If we assume that this was formed from a compound like glyceric acid, so we should consider this in as we do it in carbohydrate chemistry. This compound then will get named as L tartaric acid. Therefore, we get ambiguity in identifying the correct compounds. So, in the following slide, we will see what happens is when we do a sequence of reactions on a given compound. Suppose we take a compound which is D-glyceraldehyde. I am drawing it in the wedge dash representation. This is D-glyceraldehyde. So, if we oxidize this molecule to convert the CHO group to CO2H group, what we would get is this one. So, this is D-glyceric acid. And then we do a reduction of CH2OH to methyl. So, what we get is this compound. So, this compound is called lactic acid. If we draw the Fischer projection of this compound, this would turn out to be this one. Therefore, if you look at this molecule, then this should be termed based on the orientation as D-lactic acid. But if we do a different sequence of reactions, we first reduce the CHO to methyl, what we get is this compound. And then if we oxidize CH2OH to CO2H, we get this compound. So, therefore, if we then convert it into the corresponding Fischer projection, what we get is this one. And then if we just do in plane 180-degree rotation, we get the Fischer projection like this. So, we have got the same compound lactic acid, but now the configuration is L. So, what we have achieved is by breaking or making any CC bond, we have been able to change the absolute configuration of a chiral center from D to L lactic acid. Therefore, this method of designating the chiral centers using D and L is inappropriate for many different systems. So, these shortcomings led us to always stick to the R and S notations for the chiral centers. So, from here we will continue in the next lecture. Thank you.